Thank you for having me. It's great to be here. Well, not really here, but yeah. So I'll be talking about stuff that I did for my thesis. Um, let's see. Yeah. So nobody has really talked about Iwasawa theory, so I think I should give a brief background. So what is Iwasawa theory? It really involves studying Galois modules over infinite towers of number fields. And though it might appear a little counterintuitive, but really studying class groups or Selmer groups over particular number fields is often very hard. But if you can put them in nice towers, then their properties stabilize, and therefore studying them becomes easier. So the so we'll consider the simplest case. We'll start with the rational numbers, and we'll construct a tower, a ZP tower. And what that really means is that every layer, Qn, is going to be a unique subfield of Q adjoint the p to the n plus 1th roots of unity. And Galois group of Qn over Q is a cyclic group of order p to the n. And now when you take the inverse limit, you get Galois Q cyclotomic over Q. So Q cyc is the cyclotomic extension, and the Galois group is isomorphic to the p-adic integers. And the cyclotomic extension that I've just constructed for you is unique. And in fact, for Q, this is the unique ZP extension, which is contained inside of Q adjoint mu p infinity. Now, there was nothing very particular about Q. You can play the same game for any number field, and you will always be able to construct a cyclotomic ZP extension the way I did. But it is not necessary that this ZP extension is going to be the only ZP extension. So later on in the talk, we will see other ZP extensions. So in particular, if your field is not totally real, you expect, if your field is not totally real, you know that there are infinitely many ZP extensions. But when your field is totally real, you expect there to be this only one ZP extension, which is the cyclotomic one. And here is a quick field diagram just to sort of highlight that you can think of the ZP extension either as a subgroup or as a quotient, and that really kind of plays a very important role when we are studying properties. Right. So I will be talking about this technical object called an Iwasawa algebra. So though my definition will be for profinite group G in general, but if you're not familiar with it, you can just think of G equals ZP, because that's going to be the most important thing for today. So you have the inverse limit of these formal groups, ZP bracket G mod H, and the inverse limit is running over all open normal subgroups. And this produces what we call the Iwasawa algebra. The point is that just studying modules over like ZP bracket G is kind of hard. So over the formal group rings is hard. So you need to look at this completion. Yeah. In the particular case, when G is isomorphic to ZP, you have this very nice isomorphism. So lambda gamma, which is the Iwasawa algebra, is a formal power series ring in one variable. It is ZP double bracket T, and you have this identification where gamma goes to 1 plus T. And this isomorphism actually helps in writing any module, any finitely generated lambda gamma module in this form. This is called the structure theorem. It was due to Iwasawa and Serre. So M, this twiddle that I have over here, means a pseudo isomorphism. So that means it's a homomorphism with a finite kernel and a finite co-kernel. And so you have any finitely generated lambda gamma module, pseudo-isomorphic to a free part, and then you have these torsion parts. So R is called the rank. And when R is 0, you can define two very important invariants in Iwasawa theory. One is called the mu invariant, which is just the sum of the powers ni that's appearing in the first term, and the lambda invariant, which is summation mj times degree fj. So what I should mention is that, well, this should remind you of modules over PIDs, and that's exactly the point of the structure theorem, which is even though lambda gamma is not a PID, there is a structure theorem which is very similar to that of the PIDs. So pretty much the beginning of Iwasawa theory is based on this very important result of Kenkichi Iwasawa from the 50s, I believe. And what the statement is saying is that if you take any ZP extension, not just the cyclotomic one, so for every finite layer, you can actually write down what is the size of the class group, or at least what is the size of the P part of the class group. And there's this very precise formula, which is if En is the largest power of P that divides the class number, then En is lambda n plus mu P to the n plus a constant mu. And if you're wondering the lambda and mu, whether they are the same as what showed up earlier, well, yes, they're related. You just have to choose your module accordingly. So in this case, you have to take the pro-P Hilbert class field, the module that comes from that, and you get this formula, which I find extremely fascinating. And he conjectured that for the cyclotomic ZP extension, mu should be precisely equal to 0. This is called the classical mu equals 0 conjecture. And this is only known when the number field is an abelian-Galois extension over Q. And this result is more than 40 years old due to Ferrero and Washington. And not a lot of progress has been done in this direction since. Now, I will be shifting gears for a little bit. I'll be talking about Selmer groups of elliptic curves. So if you're familiar with what a Selmer group is, you don't really have to deal with this definition. This is just the one that's convenient for us, but any definition of Selmer group that you're familiar with is okay. I will be writing Selmer, but I really always mean the P primary part of the Selmer group. And if you're not familiar with the Selmer group, then what I want to say is that it's just measuring some sort of a local global failure. And that was explained extremely well in Asher's talk today morning. So one object that we will care about is not the Selmer group over a number field itself, but instead the direct limit of these P primary Selmer groups. So we'll be thinking of the Selmer groups over our pro-P-periodic Lie extensions, in particular ZP extensions. So Mazur in 1972 actually came up with this Iwasawa theory of elliptic curves. So first, I should tell you what's a Pontryagin dual. It's just homomorphisms going from your module M to QP mod ZP. And the only reason why I have to introduce this is because it's often easier to work with compact modules than the discrete ones that I defined earlier, but this is just a technicality. And what Mazur proved was that the P primary Selmer group over the cyclotomic extension is a finitely generated lambda gamma module. Therefore, you have a structure theorem as before. And when P is a prime of good ordinary reduction, you actually expect that rank R that was showing up to be equal to 0. So therefore, you can now define a mu invariant and a lambda invariant. But what he very quickly noticed was that this mu invariant could be positive, even for elliptic curves over Q. So even though there's this broad philosophy generally that, Selmer groups and class groups are related, like they give you information about each other. So, but there was this, even though the classical Iwasawa conjecture says mu should be equal to 0, in the Selmer, in the case of elliptic curves, you had very easy counterexamples. So in 2005, Coates and Sujata actually defined a subgroup of the Selmer group that they called the fine Selmer group. I'll give the definition on the next slide. But the point of introducing this subgroup was that they really were able to predict and show in some cases that this is the right analog of the class group in this Iwasawa theoretic setting. And they conjectured that the mu invariant that you should be able to associate with the fine Selmer group should in fact be equal to 0. And one thing that I should point out is that the dual fine Selmer group is the quotient of the dual Selmer, and you actually always expect it to be lambda torsion, irrespective of the reduction type. So mu invariant is always going to be defined. And you have explicit, like it's known in some cases that it is in fact always lambda gamma torsion due to some results of Kato. And so fine Selmer group, as I said, again, I'm not going to go into the technical definitions, but this is just a subgroup of the Selmer group. And once again, we will be looking at direct limits. So we will be looking at fine Selmer groups over the ZP extensions or other pro-p-adic extensions. And so one result that I proved with my co-advisor, Sujata, was we were able to produce examples of elliptic curves, give basically a class of elliptic curves for which the Selmer, in fact, was trivial over the cyclotomic extension. So the fine Selmer was actually trivial, not just that the mu invariant was 0. So this was conditional on the finiteness of Shaw, though. But this is not what I want to talk about mainly today. If you have questions, I'll be willing to talk about it later. So here are the two conjectures that I've talked about, one in the classical setting, one in the elliptic curve setting. And if a priori they're not related, but Coates and Sujata in 2005 in that paper actually were able to show that the two conjectures are equivalent if a certain technical condition holds. And Kumar Murthy, who is my advisor, he also worked with Ming-Fei Lim and gave a different proof of this. And then Kumar just wanted me to understand if this similarity could be extended to other cases, which was, so you know that the class groups and fine Selmer groups are behaving very similarly in cyclotomic extensions. What about other ZP extensions or other p-adic Lie extensions? So some cases where we have been able to show that class groups and fine Selmer groups are growing very similarly are basically a large class of ZP extensions and also multiple ZP extensions. So these are ZPD extensions. In some non-abelian pro-p-adic Lie extensions like false state curve extensions, very surprisingly, there are non-p-adic analytic extensions where we're able to show that class groups and fine Selmer groups grow very similarly, which is kind of striking because when you move to non-p-adic analytic towers, all Iwasawa theoretic techniques fail. So being able to show this was kind of interesting. And in fact, we are also able to show that class groups and fine Selmer groups behave very, very closely or similarly in certain finite extensions as well. But what I really want to talk about today is non-cyclotomic ZP extensions. So Iwasawa actually, though he conjectured that for cyclotomic ZP extensions, mu should be equal to 0, in 1973, he was able to construct explicit ZP extensions where the mu could be arbitrarily large. And there were no known examples of fine Selmer groups over ZP extensions where mu could be positive. So I played around with Iwasawa's proof a bit, and I was actually able to show that under certain technical assumptions, the mu invariant of the fine Selmer group can be made arbitrarily large if you choose your ZP extension correctly. So very quickly, I'll outline the proof. So let F be a field, which I've said it doesn't have to be the cyclotomic field of pith roots of unity. You can basically take any CM field, but it's easier to state it this way. And you look at the maximal totally real subfield F plus, and you construct a non-cyclotomic ZP extension F infinity over F, which is Galois over F plus. So it's always going to be Galois over F. It need not be Galois over F plus, but if it's a CM field, you can do this. Then you have to show that there are infinitely many primes, which split completely in the ZP extension. Then you choose a finite set of these primes and construct L in the way that I've written on the slide. So this is a degree, so this is a Z mod PZ extension over F that you construct, and also then adjoin that to the F infinity that you constructed earlier and construct a ZP extension over L. So this ZP extension over L also has infinite splitting of a prime, which is not happening in a tower like the ZP extension, like the cyclotomic extension. And this is where most of the work goes in. You have to relate the P rank of the fine Selmer group to the P rank of the class group. And once you're able to do that, then you can use some very standard techniques to go from the P rank to the mu invariance. And using Iwasawa's result, you can actually show that the mu invariant of the fine Selmer group is going to be bigger than equal to a constant times t, where t is the number of prime ideals that I chose to construct my L, plus another constant C2e over F. So C1 is a constant that's either 1 or 2, and C2 is another constant which is very explicit and basically depends on the number of bad primes your elliptic curve has over your base field F. And that produces lots of examples. So basically, if you give me any n, I can choose my t accordingly and produce for you a cyclic extension and a ZP extension over it, such that the mu invariant of the fine Selmer group becomes arbitrarily large. And I should mention that this can actually also be extended to other propiatic Lie extensions. And I'll not go into the details, but if you can come up with a propiatic Lie extension of a number field where you can show that the mu invariant is arbitrarily large, then now there's a general strategy to show that the mu invariant of the fine Selmer group can be arbitrarily large. So the definition of the mu invariant is slightly different from what I've given before. And maybe one last thing that I should mention is that this is really sort of telling you that if you want to go from the class groups to the Selmer groups, or from Selmer groups to the class groups, probably looking at fine Selmer group in the middle is a good idea, because so fine Selmer group is in a way interpolating between the class groups and the Selmer groups, and going from class group to fine Selmer group at least appears to be a little easier than going straight to the Selmer grids. And I think I'm out of time, so I will stop here.